Hi everyone, my name is Myat Maung, and I would like to present my project on diagnosing VLM grounding and planning failures in safety critical visual reasoning domains. So take this image as an example. The the stern of the ship is sinking with a containment boom at the front of the ship. But Lava and Quinn both agree that there's no distress sign in this ship, or that no immediate salvage plan or action is required, and that all visual evidence is clear and unambiguous. VLMs are increasingly getting proposed for safety critical perception tests. But does that mean that a model can correctly perceive an image? And does that mean a model can reason and plan correctly given a disaster scenario and information on how to plan? And how do these affect downstream planning? Maritime disaster is a perfect test bed because it tests both a model's vision and reasoning abilities, which is what we did in this work, which is testing vision language models on maritime shipwreck classification and planning operations. So the dataset contains of 110 shipwreck images, namely 42 aground, 19 capsized, 33 sunken, and 16 on fire, which are web scraped from Wikipedia. Along with the VLMs as a baseline, we also decided to take training-free hallucination mitigation methods to see if it could potentially improve VLM's abilities. So decoding with generative feedback, DEGF, generates an image from the model's own description and then redecodes the model output so that it agrees with the real image and not the hallucinated image. And only one layer intervention uses text to visual divergence to find the layer most responsible for ignoring vision and then contrasts it against a pass with that layer suppressed. Both, both have been tested on general benchmarks, but have not been tested in this maritime shipwreck classification and planning domain. So for our first experiment, we test the model's ability to classify the shipwreck images. So we feed the data set through two different VLMs, Lava and Quen, across three decoding methods, namely baseline, DGF, and only, across six prompt variants, which is direct JSON one direct JSON guided, variants of chain of thought, descriptive a descriptive prompt, and an assertion guided prompt, which is essentially information presented as assertions. And the models is then asked to classify the disaster state of the ship, the type of the vessel, size of the vessel, and cargo type, if any, is present. These labels are then taken into account and judged against human labeled ground truth using a panel of LLM as judges via majority vote. So for the results, the first key takeaway is that model's choice seems to matter more than decoding method. If we look at both heat maps, we can see that no matter the type of prompt or decoding method, Quen almost always does better than Lava. And if we look at across different models and different decoding methods, it seems that performance varies depending on the model and prompt. With Quen 3, with an assertion when their baseline with an assertion method prompting seems to be outperforming everything else with a 77% on combined accuracy. So the next question is, can a VLM reason and plan correctly given its predictions? So we take Quen as VLM as the backbone and test it against three different assertions, uh, three different as plans as assertions. So we have specific assertions which basically detail how a plan should be and how chips can be salvaged. And we have vague assertions, which basically details almost very little, but just takes up word space. So something like conditions at the scene may need to be assessed before any action is taken, which is very generic. Whereas in specific assertions, we'll give what specific conditions for what specific actions. And then there's no assertions, just to see how the natural model performs. And then the model is asked to come up with a salvage plan generation on how to assess the site, how to recover materials, what resources would use, what are the risks, and so on. These plans are then judged using three metrics, which is assertion coverage, meaning how many assertions the model used correctly, and sequencing if the model sequence the steps correctly or not, and if the method is valid and specific enough. These are judged using a deterministic match or LLM as judge. We haven't tested for uh, sequencing and method validity, but for assertions, we test if a model can use correct assertions based off of ground truth, or we also compared it against what it the model predicted tracked on assertions. So the key takeaway is that giving the right knowledge base to the model will help better specific planning. So if we look at the F1 score right here, we can see that specific outperforms fakes and none by a huge percent. And it becomes more apparent when we look at the predicted track instead of ground truth assertions, which suggests that a model classifying correctly may shape the model's downstream planning and reasoning the ability to do that correctly. So the lessons learned is that backbone choice dominates training free decoding fixes and don't may not necessarily transfer in this domain. Plan stays Model generated plans may stay coherent with the model's own misread classifications and not with reality, or that the right knowledge base to the model may be able to nudge the model to better specific planning. For future work, we would like to come up with better measures on plan quality and finish our test on specificity and so forth. And it would be interesting to see which classification fields affects downstream planning the most, and to do more case studies and failure analysis on each type of experiments and validate the judge system so that it aligns with human agreement. Thank you. I would like to take this moment to thank Dr. Katya Sagara and Dr. Dana Hughes for being my amazing mentors and guiding me throughout this whole process. I would like to thank Office of Naval Research for funding this project and Rachel Burchin and Dr. John Dolan for making this possible. Thank you very much.